Welcome to Around Space. I'm Kent Miller. Today we're going to be talking about Dragonfly. Now this is a very unique telescope that actually it's a bundle of several telescopes. Kind of looks like or reminds one of the eye of a small insect, which contains many lenses. Anyway, I'm delighted to have with us here Dr. Bradford Behr. He's an astronomer and optical engineer. In 1992, he got his bachelor's in astronomy from Williams College in Massachusetts. In the year 2000, he got his PhD in astrophysics from Caltech. From then until 2003, he worked at the McDowell Observatory in Texas. And from 2003 to 2007, he worked at the U.S. Naval Observatory here in Washington, D.C. Since then, he's moved off into the private sector, bringing spectroscopy down to Earth. Welcome back to this table.
Thanks, Kent. It's great to be here.
Tell us about Dragonfly.
Dragonfly. Now, just to be clear, I'm not working on Dragonfly myself, but it's something that I've read about in the astronomical literature, and it caught my attention and my imagination because it's a very clever, small telescope project. Most astronomers generally want bigger and bigger telescopes, a larger light bucket to collect as many photons as possible to be able to see fainter, more distant objects. But even with all these 10-meter diameter telescopes in operation and 20 and 30-meter telescopes being constructed right now, there's still a very important role for small, specialized telescopes that are designed to do one thing and do it really, really well.
Well, let's talk about that one thing.
Yes.
Because
we'll set the stage here.
Right, and then we'll talk about the requirements for the telescope.
Right.
Yeah.
So over the past several decades in astronomy research, we're getting a better idea of how galaxies are formed, how we got from the very smooth, uniform distribution of matter in the universe back in the Big Bang era and immediately thereafter, to the very clumpy universe today, where most of the matter is concentrated into galaxies, and within the galaxy concentrated into stars and planets. And the emerging consensus is that galaxies like our own Milky Way were formed out of smaller building blocks, miniature dwarf galaxies that got pulled together by their own mutual gravity and settled down into, in the case of the Milky Way, a spiral disk. And this
now in the space between galaxies, there's still some matter and maybe some smaller clusters of matter.
Clumps, some of these leftover gas clouds, and particularly in the area, in the vicinity of large galaxies, we would expect, from all the computer simulations that have been done, we would expect to find some leftover chunks or clouds, these building blocks, these miniature dwarf galaxies that haven't yet fully been absorbed into the local heavyweight galaxy. The clouds of Magellan, these two miniature galaxies that you can see from the southern hemisphere, are examples of this. And
they're in orbit around the Milky Way.
They're orbiting the center of the Milky Way, taking hundreds of thousands of years hundreds of millions of years to make full orbits.
Are they close enough that tidal forces will tear them apart?
Well, those particular dwarf galaxies have enough of their own gravity that they're going to stick together. But smaller dwarf galaxies have and continue to be ripped apart. The gravity's stronger on one side of this dwarf than the other, and so those stars get pulled away. And looking in detail at the local neighborhood of our Milky Way, we see a lot of evidence, tidal streams, these long ribbons of stars that are kind of leaking away from either end of a galaxy.
I see.
And oftentimes even tidal streams with no dwarf associated with them. It's been totally ripped apart into one of these streams. And the question then is this same process happening around other more distant galaxies?
Right.
If so, then that is an important clue for how this whole building block construction process took place billions of years ago.
Apart from what we observe, is there an expectation that we have as to how many of these dwarf galaxies are out there?
There is, and that's based almost entirely on these computer simulations.
I see.
And which, like all simulations, they may or may not be correct, or they may be leaving out key details, but a lot of very sophisticated physical computation has been done, and there is what's often referred to as the missing dwarf problem, that there should be more of these leftover building blocks than we're currently observing.
So the rate at which the mass clumped together into large galaxies, we would expect would not have cleaned up all of the dwarf galaxies.
There's always going to be some leftover. There's going to be.
And we don't see them?
We don't see them, although as the technology in our telescopes improves, we are seeing more and more of them in our local neighborhood. And this Dragonfly telescope was the design and construction of it was motivated by the need or the desire to be able to look at somewhat more distant galaxies to look to see if they've got some of these dwarf companions orbiting around them as well. And many of the better known nearby galaxies do have dwarf companions, but we're only seeing the big ones. The question is how many smaller and fainter ones are also present.
I see. Let me ask about galaxies tend to be rather extended objects.
Yes.
You know, so I would think the big 10-meter scopes, which tend to have narrow fields of view, might not be the right equipment.
Exactly. They provide a great telephoto view, but you want a portrait view in order to see the whole family portrait, if you will. The other challenge, though, the other problem with big modern telescopes is that there's a lot of scattered light inside of them. A lot of these big telescopes are made up of many, many mirror segments that are put together like a big jigsaw puzzle. And the edges of those mirrors will bounce light off in a random direction.
This we call stray light?
Stray light. Diffraction is another physical phenomenon where light tends to bend around objects, like the truss work.
Any sharp edges.
Any sharp edges in the middle of the telescope aperture will make down at the focal plane where the camera is taking an image, you end up with spikes. It looks like a 4-pointed or 8-pointed star.
The truss that holds the diagonal mirror.
That central, the secondary mirror.
Right.
That causes big problems if you're trying to pick up these faint objects, because if you see a little smudge of light in one of your pictures, maybe it's a dwarf galaxy, or maybe it's just light from this bright star over here bouncing off some part of your telescope.
I see. You black the inside of the telescope.
Yes, but
they're what we call light baffles.
Light baffles. Yeah, you do everything you can to reduce the scattered light signature, but even with the best baffling and the best stray light suppression, these diffraction effects are still going to come into play.
Okay.
So this team of astronomers, it's a joint project between Yale and University of Toronto, came up with an idea of sort of going back to the 19th century. Back in the old days, telescopes were all refractive. They had a lens and a long tube and then an eyepiece at the end. Those
basically just a bigger example of what Galileo was using.
Exactly. Now, around about the 20th century or late 19th century, those were superseded by reflecting telescopes with a large mirror, and there are various good reasons for that. It's a lot easier to make a big mirror than a big lens. They can be a lot more compact for a larger aperture, but the reflecting telescopes have these diffraction and stray light issues.
Right.
So what the
in this country, we actually have a fairly large one. I think there was a businessman in Chicago named Yerkes.
Right.
Yerkes, and he left a grant of money to build.
And the University of Chicago built a telescope that had a 40-inch objective lens, the big lens at the front. Yeah, a little bit more than the yard. That's,
dear.
that's a good-sized piece of glass.
Yes.
But it pales in comparison to the 30-foot diameter of modern reflecting telescopes.
Yeah.
So this team of astronomers who are interested in finding the missing dwarfs sat down to think about it and realized, oh, a refracting telescope would actually do much better because it doesn't have that central obscuration to cause refraction, and that there are a lot of very high-tech coatings you can put on the glass surfaces so that anti-reflection coatings, they're called, so that the light has a sort of smoother transition going from air to glass or from glass to air, and there's always a little bit of reflection, even if it looks transparent, there's a little bit of light bouncing off of any plate glass window.
Right. Well, the coating would be specific to a particular wavelength.
So there's a technique where you put down many layers of sort of intermediate index or glass or coatings that have a certain optical characteristic, are called dielectric coatings.
Okay.
And those are, as you say, tuned to a specific wavelength. But there's a new technology that uses nanostructures, little pyramids that are smaller than the wavelength of light. And those work much better over a wide range of wavelengths.
Oh my.
And this is not something that was invented by astronomers. It was invented for professional photographers. And because they don't want lens flare messing up some photograph. And as a result, you can very easily, off the shelf, walk into a photo store and buy a really good telescope called a telephoto lens with this anti-reflection coating. So what the astronomers in question did was they got initially 8 of these telephoto lenses, and they've since added on 2 more, and mounted them all in a solid steel framework, so they all point in exactly the same direction, and then attach a CCD camera, charge-coupled device. It's a digital camera.
Right.
Attached one CCD camera to each of the telephoto lenses, creating the Dragonfly Array.
Right.
And it's not a big telescope, but it still does the job very well because of the anti-reflection coatings, and because it actually turns out when you're looking at an object that's an astronomical object, a galaxy that's spread out,
Right.
A small telescope will work just as well as a large telescope.
The field of view.
Because the field of view is wider, even though you're not collecting as much light with a smaller aperture, more light is being focused onto each individual pixel. And so
Right.
you end up with the same number of digital data counts in each pixel of your image as you would with a larger telescope.
Now, my understanding is that each of these telescopes, the fields of view overlap.
Yes, that's an important part of
Right.
this particular telescope implementation. Other people have used arrays of camera lenses or arrays of smaller telescopes, but in many cases those are...
So you're not creating a mosaic.
Right.
There really are overlapped.
You want all of these duplicate images right on
Stacked,
top of each other.
Stacked, if you wish.
Because then you take the digital image from each of the cameras and you can merge them together in order to be able to see things that are fainter. You improve the quality of the image by putting them all on top of each other.
Now, my guess is that aligning them pixel for pixel is too much.
It's
too hard.
It's too hard to do with the actual telescopes, but computers are very good at taking an image and sliding it over by 1 pixel and seeing if it lines up and trying the other way. A lot of trial and error to get the two images right on top of each other, and then bring in a 3rd image, and then bring in a 4th image.
So if you had a guide star, that would help you.
Especially if there's a bright object that you can use sort of as your fence post, as your reference point.
Yeah.
So they were able to create this brand new telescope in relatively short order because all of the components were commercial products. They didn't have to...
Basically off the shelf.
Off the shelf. It's less expensive because the camera company has already done all the development work. And these are not cheap lenses. I think they run for about $10,000 a piece, but that's still cheap compared to building a brand new telescope for a couple $1 million. And They've, I think, only been in operation for a year or so at this point. But even in their initial data collection, they've been finding some really interesting stuff. One of the first places they pointed was at the spiral galaxy M101, which is a lot of amateur astronomers like to take a picture of it, very photogenic. And somewhat appropriately, they found 7 dwarfs, 7 faint smudges of light in the immediate vicinity of M101 that no one had ever seen before, because they were those blobs of light were too faint and too spread out to show up clearly. If you had known exactly where to point Hubble, you might have been able to see it. And I think they did, in one of these cases, they went back through the Hubble archives and found that someone, in fact, had taken a picture of one of these dwarfs, but hadn't realized what it was because they were looking for something else.
Sure.
That's
why we have archives.
That's why you keep everything and never throw a single data set away. The Coma cluster is another large collection of galaxies, and they went and took some very long exposures. And often what they do, not only do they have the 8 or 10 cameras all taking a picture of the same part of the sky, they will take a picture, take another picture, take another picture, keep repeating at that same part of the sky, and then add the images together.
Now the Coma cluster is hundreds or maybe 1,000 galaxies.
Yes, it's one of the big ones out there, all swirling around each other.
Yeah.
And it turns out that there are even more of them than we thought. They found.
So you're expecting a large population of dwarfs in there?
Quite likely. What they found, I think they turned up some dwarfs, but just as interestingly, maybe even more so, they found a whole lot, several dozen galaxies the size of our Milky Way, but with 1,000 times fewer stars, and therefore 1,000 times fainter, so that no one had really noticed them before. So that's a whole new interesting observation to throw into the mix. Some of the theorists who have been doing these computer simulations said, "Oh, yeah, actually we expect to see something like that, but we thought our simulations were wrong because no one's ever seen anything in the real universe." So it may turn out to be that that dwarf is something of a misnomer, that there are large but very sparsely populated shadow galaxies out there that are remnants from the early stages of galaxy formation.
Well, if you're saying a galaxy of a certain size but 100th of the number of stars, could one make an assumption, this is kind of a leap, but can one assume that the percentage of the mass of that galaxy would be dark matter?
Quite possibly, yes. So dark matter, just to bring everyone up to speed, is this. There's something out there that's got gravity, and it's not normal protons, neutrons, and electrons, but it makes up.
Well, not luminous.
Not luminous. So yeah, dark matter in general might be baryonic matter, protons, neutrons, and electrons, like what we're made of. Right. That just isn't glowing. But in addition to that, there's very strong evidence now that there's something else out there that's subatomic particles, or something not what we think of as normal matter, that makes up a large fraction of the universe, and that we only know about because of its gravitational pull on the stuff we can see.
Right. So if we look at the rate at which a galaxy rotates, the spiral galaxies, we can get an idea of that from the Doppler shift. And we'd guess that to hold it together gravitationally, there'd have to be much more mass than the luminous mass that we see.
Pulling towards the center. If it was just what we see, and it's spinning at a certain speed, it would fly apart.
Spinning too fast to stay together.
Exactly.
Yeah.
So there must be something else there that's pulling in gravitationally. But is it brown dwarfs? Probably not. People say, "Oh, black holes," but black holes are actually. You can usually see a black hole.
They give off a lot of light.
They give off a lot of light from outside the event horizon.
Because anything falling in
gets heated up and emits X-rays and lots of other radiation. So, the whole role of dark matter is a key part of this jigsaw puzzle we're putting together of how the galaxies form. So these newly discovered galaxies may in fact have the same amount of mass as the Milky Way, just fewer luminous stars. That's something to be determined. This whole area, and the Dragonfly measurements in particular, are cutting edge science where we really aren't sure yet.
Right.
These are initial measurements, and it's very suggestive, it's very exciting, but it'll be many years, probably decades, before it all sorts out and we
Right.
Can figure out
Well,
truly what's going on.
I used to be an experimentalist, and usually what we look for is sources of error or alternative explanations for for our data.
Right.
And one possibility that comes to mind is perhaps these dwarfs are actually normal-sized galaxies, but just much further away.
That is certainly
that just happen to be in your field of view.
right. Yes, that is something that the researchers admitted freely when they wrote their paper about the 7 dwarfs around M101. They pointed out that they could easily be background galaxies.
Right.
And they are planning further measurements and observations, not just with Dragonfly, but with larger telescopes, to, for instance, look at the spectrum from each of these galaxies, and from which you can measure not only the chemical composition, what they're made of, and what types of stars are there, and that will, in some cases, differentiate between a faraway big galaxy and a nearby small galaxy, but also the redshift. As most of our viewers know, the further something away is in the universe, the faster it's moving away from us.
That's called the Hubble.
The Hubble constant
yeah.
is the number that tells you that relationship between distance and velocity.
The redshift, yeah.
So, if we measure the redshift for these newly discovered galaxies, and they are moving away 5 times more rapidly than M101, then okay, they're probably
5 times further away.
right.
Yeah.
If they have the same
Similar.
ballpark, similar redshift to M101, then they're probably part of the M101 system
So maybe
and
in orbit.
are
Yeah.
true dwarfs. And yeah, if we can measure the velocities precisely enough and see some of them moving away and some of them moving towards us, then that tells us about the dynamics of these things as they orbit around M101.
Okay, let's talk a little bit about tidal forces.
Yes.
Within the solar system, we have the concept of a Roche limit. For example, the moon is outside of this limit, so that it can stay together as a single body held together by its own gravity.
Right.
But if, let's say, you take a big ball of sand and bring it closer to the Earth, at some point the tidal force is enough, the sand starts getting removed, and you get this big stream of sand that goes all around. It was almost like the rings of Saturn.
And that's
Right.
The rings of Saturn, and I think the asteroid belt is considered an example of a body. It wasn't ripped apart by Jupiter's gravity, but Jupiter's tidal influence meant that all those rocks couldn't ever glom together into a single body.
Right.
At least not a single big body. There's some pretty big asteroids, but so yes,
the line I'm trying to get to is that if a dwarf galaxy gets close enough to a mainstream-sized galaxy that at some point the tidal forces would pick up the stars and start scattering them around like the rings of Saturn.
exactly,
right?
and then eventually
big streams of stars.
Those streams of stars would settle down, and they'd essentially become part of the galaxy, and there are actually this
part of that rotating disk.
Part of that rotating disk. The disk, a lot of people don't realize there are actually 2 disks, the thin disk and the thick disk in the Milky Way galaxy, and we can tell the difference between the 2 of them, not just because of the measured thickness, but they seem to be populated by slightly different types of stars with a different chemical composition, different percentages. I mean, they're all hydrogen and helium primarily, but the heavier elements.
What we call metallicity.
Metallicity, the metals. For astronomers, everything from lithium upwards is a metal. Oxygen is a metal. Nitrogen is a metal. That's a little bit weird for
yes.
Terrestrial context, but the proportions of, say, calcium to iron differ slightly depending on where that star was formed. And so this thick disk has a slightly different average chemical composition than the thin disk, suggesting that those stars formed in a different environment and then immigrated to the Milky Way instead of being born in the thin disk and staying in the thin disk.
They may have a different age.
And they do
different origin.
Generally tend to be older, as best we can tell. Wow. So yeah, that the thin disk and the thick disk, and then the Milky Way also has what's called a halo of stars that are on completely random, wacky orbits, sort of like a circular or spherical swarm of bees all buzzing about. Those tend to be the very oldest stars, and perhaps were part of a totally separate galaxy, that dwarf galaxy that came in at an oblique angle to the plane of the Milky Way, and it fragmented, and then the stars all just
turned into a swarm.
And the stars last for a long time, even after they get ripped apart from all their compadres.
Sure. Now the stars in our neighborhood are mostly what, third generation, fourth generation, high metallicity.
Exactly.
We're made of
we're made of the former innards of a star that went supernova and had created all those metals through nuclear fusion, and then reseeded the gas clouds in order to eventually form planets and people and all those good things. But yes, the somewhat backwards, as a lot of things in astronomy are. The most recent stars are all called population 1, and the Sun is considered one of those. The older stars are population 2, and there's a semi-hypothetical population 3, stars that formed before there were hardly any metals at all.
All righty. Well, thank you so much.
Thank you, Kent.
All right. That was Dr. Bradford Behr. He's an astronomer and optical engineer talking about Dragonfly. So thank you for joining us, and see you next time.